Alrighty, so far we've seen adding and subtracting and scalar multiplication with matrices. In this video we're going to learn how to times two matrices together, and adding and taking were pretty normal. Timesing matrices is really weird, but it will make sense once we do enough practice with it. If you look at this formula, you're going to probably freak out because it looks awful, but what makes more sense is just doing a bunch of examples and you'll see how it works pretty quickly. So when we times two matrices together, what we have to do is we have to check the order of those matrices. So both these are 2 by 2s. This one here is a 2 by 3, and then this last one here is a 3 by 3. So let's suppose we're trying to find A times B. What you'd be checking for is, do the middle two numbers match? In this case they do, and that means we can times these matrices together. Now if those two middle numbers don't match, we can't actually do the multiplication. It's impossible to do. Now, the resulting matrix that you get is the other two numbers. So in this case, we're going to get a 2 by 2 as our answer. And we'll see how this works in practice. So we're going to do A times B, and I'll write out what those matrices actually are. So that's 1, 3, 2, 5 times 2, 1, 0, 4. Now, what you have to do when you times matrices is sort of pair up each row and each column. So we're going to go here first with the top row and then the first column of those matrices. So what we're going to get is 1 times 2 as our first little bit there, plus 3 times 0. So you sort of pair up each one. You do the first ones together and the second ones together. That there is the very first number in our matrix, whatever that ends up being. For our next entry, we're going to be doing this. So we're going to be making that pair, 1 times 1, plus 3 times 4. All right, next one we're going to do. So we've done the two top ones. We're now going to do the two bottom ones. So there we go. All right, 2 times 2 goes on the top, plus 5 times 0. And very last one, we're going to get 2 times 1 plus 5 times 4. And we just got to see what this all ends up being. So that first entry is going to be 2. And the second entry is going to be 1 plus 12, so 13. Third entry is going to be 4. And the last entry, 2 times 1 plus 5 times 4, that'll be 22. So that's what we do when we get A times B. Now, if matrices work like normal numbers should work, then in theory, if I do B times A, I should get the same thing. Let's check out. So 2, 1, 0, 4. That's our B matrix. And I'm going to be timesing it by 1, 3, 2, 5. Alrighty, Roo. So let's do this. 2 and 1 with 1 and 2. So we're going to get 2 times 1 plus 1 times 2 as our first little bit. Next one we're going to do is 2 with 3 and 1 with 5. Next one that we're going to do here is the bottoms. So get rid of that. I'm going to do 0 and 4 with each of these. So 0 times 1 plus 4 times 2. And then last one we're going to do is 0 times 3 plus 4 times 5. And if we simplify down all these numbers, we'll see what we get. So that very top left entry is going to be 2 plus 2, which is 4. And then we're going to get 6 plus 5, which is 11. Then we're going to get 8 in the bottom left and 20 in the bottom right. Now, I don't know about you, but last time I checked, 4, 11, 8, 20 was a different matrix than 2, 13, 4, 22. So what we've actually found out here is that if I do A times B, that is different to B times A. So in general, this is true for matrices, and it's a really good point to make. Matrices do not work like real numbers work. If you take a real number and you do like 5 times 7, that will give you the same thing as 7 times 5. But if you take two matrices, you cannot just swap the order. It actually really does matter what order you times them in. All right, let's move on. We'll do A times C, and this will be a good example of sort of rectangular matrices. 2, 1, 0, 4. 1, 3, 2, 5 is A. Times the matrix C, 1, 3, 2, 1, 4, 3. All right, so first thing we need to do is check if we can actually do this timesing. So A is a 2 by 2, and then this one here is a 2 by 3. So do the middle two numbers match? Well, yes, they do. And our resulting matrix that we get should actually be these two. So a 2 by 3 is what we're expecting AC to be as a matrix. So it should look the same size as your original matrix there. Okay, so that's exactly what we're going to do here. So again, you use the same method, 1, 3 paired with 1, 1, and let's see what we get. So that's going to be 1 times 1 plus 3 times 1 as our first term there. We're then going to be doing 1, 3 paired with 3, 4. So 1 times 3 plus 3 times 4. And then we're going to be doing 1, 3 paired with 2, 3. So 1 times 2 plus 3 times 3. Then what we're going to be doing is the bottoms. So 2 and 5 we're going to be timesing by each one. I won't actually sketch out the highlighting, so hopefully you can see 2 times 1 plus 5 times 1. Then we're going to get 2 times 3 plus 5 times 4, and then 2 times 2 plus 5 times 3. And then we want to simplify this all down. All right, so 1, 1, and 3, 1, so that's going to be 4. Then our next entry is going to be 3 plus 12. Then our next entry is going to be 2 plus 9. Next entry is 2 plus 5. Next entry is 6 plus 20. And then next entry is 4 plus 15. So that is A times C. Now let's try and do C times A. So that matrix there is going to look like 1, 3, 2, 1, 4, 3 times 1, 3, 2, 5. And we'll see if we can actually do this multiplication here. So this is a 2 by 3 and this is a 2 by 2. We check, do the middle numbers match? No. So this is impossible. There is no such thing as C times A. Can't actually do it. Last time we're going to do a C times D. So we'll take our C matrix. That was 1, 3, 2, 1, 4, 3 times our D matrix, which was 103, 1, 2, 4. And then 2 minus 1, 0. All right, so first of all, let's check if we can actually do this multiplication. This matrix is a 2 by 3. This is a 3 by 3. You check, do the middle numbers match? Yes, you're expecting to get a 2 by 3 as your answer because those are the two numbers on the outside. All right, let's do this. So, okay, it's going to be a big one. I might actually just write in what the answer is straight away, but I'll talk it through. So you got 1 times 1 plus 3 times 1 plus 2 times 2. So that becomes 1 plus 3 plus 4, which is 8. Next one, you got 1 times 0 plus 3 times 2, that's 6 so far, plus 2 times minus 1, so that's 4. Next one, you've got 1 times 3 plus 3 times 4, so we're already up to 15, plus 2 times 0, and we're going to get 2 times 3, so you got 1, 4, and 3. 1 times 1 plus 4 times 1, that's 5 so far, plus another 6 gives us 11. 1 times 0, nothing. 4 times 2 is 8, and then 3 times minus 1, so that's going to be 5. 1 times 3 is 3, 4 times 4 is 16, so we're up to 19 so far, and then 3 times 0, so 19. And that's the example of finding CD. I want to point out something really cool as well, just something you can do with matrices in general. If you do, let's say the vector like 3, 4 times by 5, 6 or something like that, that's going to be very different to doing the matrices 5, 6 with 3, 4. But the really cool thing about it is in this one, you're going to get, let's see, 3, 4. So that's going to be a 1 by 2. I always forget the way these go. And then a 2 by 1. You're actually going to get like a 1 times 1 is your answer there. And that ends up being the dot product. So you get like 3 times 5 plus 4 times 6. Whereas this one here actually ends up being a 2 by 2 matrix. So if we just did that matrix, you'd get like 5 and 3, so 15, 5 and 4, 20, 6 and 3, 18, and then 6 and 4 is 24. And if you're really careful about what matrices you can pick, you can actually generate your entire times table chart, which should probably look familiar from like, you know, the back of your exercise book or something. You know, like 1 times 2 is 2, 1 times 3 is 3, 2, 3, 4, 6, 6, and then 9. And then like it would keep going on like that forever, sort of like your standard times table chart. You can actually generate that by doing a really simple matrix multiplication. See if you can have a think about that and see what you could do to generate this 12 by 12 matrix. This kind of like square one here.